Hello, this is Calculus 1, Lecture 13A, Part 2, the min and max functions. My name is Scott Grizzard from the University of South Florida. So remember, we had this idea. This is sort of a bridge between a couple different ideas. We need to introduce and chunk this before we start talking about the integral and the definition of the integral. So recall that we had this idea of a function with a base point. So if I wanted to do the area under the curve of f from 0 to x, I would have this function that moved to the right with this base point. And this base point was always fixed. And then I was measuring the area under the curve to x. Okay. And I could do this for functions that, like this one, where everything was above the x-axis, but I could also have functions where part of the function was below the x-axis, and I would add negative area. So I have this sort of definition of area under the curve, a definition we're going to firm up next time. Okay, but in order to firm that definition up, we need to talk about a min-max function. So here's how it's defined. The min function, okay, if I've got a function defined on D, right, and this interval D, which is D for domain, and let A be some function in D, and then I'm going to A be some number, some base point, okay? Then I'm going to define the function max, fa of x, with A as the base point, as if x is greater than or equal to A, I'm just going to take the maximum of the function. The maximum at x is going to be the maximum value between a and x. So as you can see here, right, if this is a, this was the min, this was the max. So if this is a, anytime I'm within here, my max is going to be up here, right? Because f of a was bigger than everything here. But then when I get to here, f of x is going to be bigger than any of these values, so it becomes the max. Okay. So my min is defined as the minimum of f of t from t within a to x, and if x is greater than or equal to a, and if x is less than or equal to a, I want the minimum on xa. Okay, so in essence, I just want the maximum value, the maximum y between x equals a and x equals x, whatever my x is, between t equals a and t equals x. And I don't care which side those two, the a and the x, are. I'm defining it the same way on either side, but I have to have this piecewise definition just because of the way that functions have to be defined. Okay, so if I think about this, let's do some examples here. So here my function is 1 over 9 x cubed minus x squared plus 5. Now what I'm going to do, again, is I'm going to define a base point. In this case, my base point is -2. So here's my base point. Now I'm going to I want to get the output of the max function. So here's the graph of f. Now if I hit play here, right, if x is right here at 0, then the max is going to be here 5, which is f of 0. But notice as I go past 0, the function goes down again. So my max remains above. And then I hit play again, and my max remains above until I get here to this function. And then I go past my y equals 5. So my max function begins to trace the function again. Because the function is increasing, I stay up. Okay, so that's the idea, right? Here, max of x is the maximum f of t when t is between a and whatever x is. So the maximum of this, if the interval is -2 to 2, the maximum on that interval is 5. So my max of x for anything greater than anything between 0 and 2, but in particular for my max of x for x equals 2 is still going to be 5 because that was the maximum I had between that interval. Again, I can do this again. Here, I'll change my base point to positive 2, and I'll talk about, so here, right now, when I'm at 1, the max between 1 and 2, because I'm left of the base point, the max between 1 and 2 here is f of 1, because I'm going down and I'm approaching 2. Now, when I get to 2, my maximum now from 2, again, 2 is my base point, from 2 to 3 is f of 2. And now I hit play again, and then when I get to this, I go up again. So the reason that it was decreasing here is because my base point was 2. So as x moved in, closer and closer to 2, my max got smaller. Now what I'm going to do, here the base point's got to be 4, and I'm going to show you the exact same thing again. Right? Here I went to, here the max between 3 and 4 is whatever this f of 3 was. But now, if I advance it a little bit further, the max from 3 to 4, I'm sorry, 3.5 to 4 is whatever f of 3.5 was. So that becomes my max. And that's why this function kind of traces here in blue. This is my max function. As I move x this way, I get closer and closer to the base point. Now, when I reach 4, of course, the max is now between 4 and 5, right? So max of 5 is going to be the maximum between 4 and 5, and that's still going to be f of 4. It's going to be f of 4 until I reach somewhere over here where it becomes f of x again. So that's kind of how the max function works. And it's a little bit, I'm not saying it's not a little bit weird. Let's look at another one. Let's start, it's easier to think of if you don't think about these left side things. So let's do this example here. This right here as a base point of 0, and I'm doing sine of pi x over 2 plus pi over plus x over 4. So now as I move to the right, I bump, and then the function goes below the max, and then I come up here, and my new max is this one. Then I come up here, my new max is that one. Now I come up here, my new max is that one. Now I come over here, my new max is that one. Okay, so that's the thing you need to remember. Think of it, if the negative side, if the left side bothers you, that's okay. You can ditch it and still get the idea, because what we want is the big idea of this. Okay, now, the big ideas that I have are the following. If f is continuous on ax, then this max will exist because by the extreme value theorem, right? The extreme value theorem says that I achieve a max if f is continuous and if I have a closed interval. Likewise, the min will exist. So if f is continuous, then min fa and mf and max fa are both well defined. And we're going to need these functions to define AUC for continuous. We're going to need this max and min idea to define AUC for continuous functions, and then we're going to use it later to prove the fundamental theorem of calculus. So it's a small little bit, and it's kind of a leftover from Module 3, but think about these functions and play with them a little bit, because we're going to need them later. Okay, well that's it for today. Next time, what we're going to have is we're going to define the Riemann integral to get a good definition of AUC. Remember, there was a part 1 to this lecture that is also due in your notes if you are enrolled in the class. Thank you.